I'm excited to introduce SPAD, our system for video rate hyperspectral inference using single-photon sensors. Here we have a colorful dynamic scene of a rotating city. The colors of the scene can be captured by 3 spectral response channels. As we all know, however, the light from a scene contains much more information than these 3 channels. Our goal is to capture hyperspectral video with more than 100 spectral channels, spanning not only visible but also the near-infrared range, while maintaining high spatial resolution. As a solution, we propose SPAD, a scanning-based video rate hyperspectral imager. Our lab prototype achieves 123 spectral channels at 26 frames per second. Capturing hyperspectral video is challenging due to extreme light sparsity across space, time, and spectral axis. Under this low light scenario, conventional CMOS sensors have to contend with additive readout noise resulting from analog to digital conversion. Therefore, the captured hyperspectral video with CMOS sensor in compress-free manner will end up being buried by the noise. To overcome this readout noise, we leverage SPAD sensors, single-photon detectors that are inherently readout noise-free. SPAD sensor is an emerging technique fundamentally different from CMOS. Single-photon arrival on the sensor trigger avalanche process, resulting binary digital signal for photon detection. Therefore, there is no analog to digital conversion and no readout noise. Our system uses a SPAD sensor in a scanning configuration to achieve high-resolution hyperspectral imaging. We call this method SPAD, hyperspectral imaging with SPAD sensors. However, SPAD-based spectral measurements are still noisy, highly quantized, and nonlinear. Therefore, we provide theoretical guarantees for spectrum reconstruction and material classification with experimental validation and multiple full spectrum reconstruction methods. Now let's see our lab prototype SPAD camera. It is built as push-button camera system with digital micrometer device, employing SPAD sensor as choice of sensor. First, light from a scene is focused on the DMD. Then DMD selectively reflects a single column of the focus image by flipping a corresponding single column of micrometers toward image R. Next, the reflected light from the DMD first comes into the grating where the dispersion is performed, and SPAD camera captures the spectrally dispersed image of the single column. By sequentially displaying columns on the DMD and capturing the spectrally dispersed image of each column, we can acquire the whole data for reconstructing a single hyperspectral cube. In our setup, the DMD can operate at up to 20 kHz, while the SPAD sensor can reach up to 100 kHz. With this operation, the system can acquire 26 fps hyperspectral video with 123 spectral channels in the wavelength range of 445 to 910 nanometer. Here, we present results captured using our SPAD prototype operating at video rate. The raw hyperspectral video contains 123 spectral channels from 445 to 910 nanometer wavelengths. For comparison, we simulated CMOS-based capture with realistic readout noise, and below is the SPAD measurements under identical conditions. Now let's look at outdoor scenes captured in sunny conditions. We also show results from cloudy day captures to demonstrate robustness. With SPAD, we demonstrate 3 applications enabled by real-time hyperspectral video. First, we simulate scene relighting by dividing out the non-light spectrum and multiplying in new illumination. Second, we render videos as they would appear through different camera spectrum sensitivities. Third, we perform per-pixel material classification at video rate using a cosine similarity classifier and spectral dictionary. Thank you. Please read the paper for full details.